So far, we have studied the modes of heat transfer. We have studied heat conduction in solids, we have studied thermal radiation, and we have also studied convection. In convection, we have looked at forced convection and natural convection. Now, today we start with the topic of heat exchangers. The first thing we ask ourselves is, the first thing we will do rather, is to describe various types of heat exchangers. Before that, let me just restate again the textbooks and the reference books which we are following. We are following my book on a textbook on heat transfer by Universities Press. We are also following Incropera and Devitt, the fundamentals of heat and mass transfer. These are two books which we are closely following. So, if you miss some part, or you are not able to take down some notes, or you are not able to take down a figure, generally you will find a figure which is very similar to what we are showing in one of these two books. Now, the first thing we ask ourselves is, what are heat exchangers? Well, heat exchangers are devices in which heat is transferred between two fluids at different temperatures without any mixing of the fluids. There are two fluids, one is hotter than the other, they are at different temperatures. Heat is transferred from the hot fluid to the cold fluid. A device in which this happens is called a heat exchanger, and this occurs without any mixing of the two fluids, that is, the hot fluid does not mix with the cold fluid. The heat transfer takes place without any mixing of the fluids with each other. That is called a heat exchanger. Now, broadly speaking, there are three types of heat exchangers, or the various hundreds of heat exchangers which are built and hundreds of geometries, etc., which are built. There are three broad classifications, or three types of heat exchangers. The three types are: number 1, what is called as the direct transfer type; number 2, what is called as the storage type; and number 3, what is called as the direct contact type. These are three broad types of heat exchangers. Let us look at each of these for a moment. First, the direct transfer type. A direct transfer type of heat exchanger is one in which the cold and hot fluids flow simultaneously through the device and heat is transferred through a wall separating the two fluids. I repeat, a direct transfer type of heat exchanger is one in which the cold and the hot fluids flow simultaneously through the device and heat is transferred through a wall separating the fluids. All right. Let us look at an example of a direct transfer type heat exchanger. The example we are going to look at is a very simple one. The particular direct transfer type of heat exchanger we are looking at is what is called as a concentric tube heat exchanger. So, we say it is a direct transfer type concentric tube heat exchanger. The words concentric tube describe the geometry of the heat exchanger, that is, there is one tube inside another tube. This is the one tube that is inside, this is the outer tube here. All right. So, and they are concentric to each other, that is why it is called a concentric tube heat exchanger. Okay. And the two fluids, the one fluid, in this case the hot fluid, flows through the inner tube. It is shown here, it is entering the inner tube on the left hand side, flowing along the inner tube and getting out here. The hot fluid is leaving the heat exchanger here. The cold fluid is entering the outer tube, flowing through the annulus and then exiting out here, flows along the whole length and then exiting out here. So, one fluid flows inside the inner tube, in this case it is the hot fluid. The other fluid, the cold fluid, flows inside the annulus, and that is why I used the word concentric tube heat exchanger. It is also referred to sometimes as a tube in tube heat exchanger. All right. Now, the heat transfer in this heat exchanger takes place across the wall of the inner tube. So, the hot fluid is flowing inside the inner tube here, the cold fluid is in the annulus here. So, the heat transfer is taking place like this from the hot fluid to the cold fluid across the wall of the inner tube. You follow? This is where the heat transfer is taking place. And as the cold fluid flows in the annulus, it is picking up heat, its temperature is rising, and as the hot fluid flows along the length, it is giving up heat, and therefore, it is dropping in temperature. So, this is the heat transfer surface. This is the heat transfer surface where heat transfer is taking place, the wall of the inner tube of the heat exchanger. So, this is a direct transfer type heat exchanger. Both the fluids are flowing simultaneously through the heat exchanger, and heat is flowing across the wall of the inner tube from the hot fluid to the cold fluid. There is of course no mixing of the fluids. This is one type, and this is the type that we will really be studying in detail. Now, we come to the second type, broad classification. The second type of heat exchanger is what we have called a storage type heat exchanger. Now, let us look at the description of it. A storage type heat exchanger is one in which the heat transfer from the hot fluid to the cold fluid occurs through a coupling medium in the form of a porous solid matrix. I repeat, a storage type heat exchanger is one in which the heat transfer from the hot fluid to the cold fluid occurs through a coupling medium in the form of a porous solid matrix. The hot and cold fluids flow alternately through the matrix, the hot fluid storing heat in it and the cold fluid extracting heat from it. You follow? The hot and cold fluids flow alternately through the matrix, the hot fluid storing heat in it and the cold fluid extracting heat from it. Now, let us look at a sketch, so that we describe this heat exchanger a little better. What I have shown in the sketch is a single matrix storage type heat exchanger. All right. The cross hatching shows the porous matrix. The porous matrix, for instance, may be pebbles with passages through them, or it may be some brickwork with holes in it, porous brickwork through holes in it. It could be loosely kept, some finer material loosely kept, etc. Basically, something through which fluid can flow, a gas can flow or air can flow, and something which will absorb heat or give up heat when the hot fluid or the cold fluid flows through it, as may be the case. All right. So, this is the porous matrix, and what we have here, the circles with crosses on them, are valves which can be opened or closed. So, let us just what you call give them a nomenclature. Let us say this is valve A, this is valve B, this is valve C, and this is valve D. All right. Let us say first of all that during the operation of this heat exchanger, valves A and D are open and B and C are closed. So, obviously, the hot fluid can enter here if this valve is open, go through this porous matrix and come out through D. If it does this, it is going to give up its energy, its heat to the material of this porous matrix, and this matrix is going to heat up. We do this for some time, then during this period, of course, B and C are closed. Now, after doing this for some time, we close A and D and open B and C, so that the cold fluid starts to flow through this matrix, and the cold fluid picks up heat from this matrix, gets heated and then flows out. So, one by one the hot fluid flows through, stores heat in the matrix, the cold fluid flows through and picks up heat from the matrix. So, that is why this is called a storage type of heat exchanger. All right. There are many versions, of course, of the storage type. This is the simplest type. We just want to show one here. And then the third type of heat exchanger, third broad classification, is what we call as a direct contact type heat exchanger. A direct contact type heat exchanger. What is this? A direct contact type heat exchanger is one in which the two fluids are not separated. If heat is to be transferred between a gas and a liquid, the gas is bubbled through the liquid, or the liquid is sprayed in the form of droplets into the gas, and once it is sprayed in the form of droplets, heat gets transferred in the direction between the hot fluid and the cold fluid, or the gas is bubbled through the liquid, in which case also heat gets transferred between the hot fluid and the cold fluid. All right. Let us again illustrate this with a sketch to show a direct contact type of heat exchanger. Here is a direct contact type heat exchanger now. This is a fluid A. Let us say it is a liquid which is entering here. All right. So, this is like a shower head, it is entering through the shower head here, and drops of this liquid come out of the shower head. These drops flow through like this and ultimately come down and collect here and go out of the heat exchanger. The other fluid, let us say it is a gas, flows in here and flows upwards through this heat exchanger. So, let us say it is water and air, for instance. So, the water is being sprayed in the form of drops and the air is flowing upwards through this heat exchanger. Now, if for instance the water is hotter than the air, obviously heat is going to flow from the water to the air, or if the air is hotter than the water, the reverse will happen. All right. So, this is what we call as a direct contact type heat exchanger, in which one of the fluids is deformed. Deformed means put into the shape of, say, droplets or bubbles, and then the heat transfer takes place. After the heat transfer takes place, it is all collected and flows out. So, the droplets all get collected here and flow out. So, that is why we call it a direct contact type heat exchanger, because the process of heat transfer here occurs in this case at each drop. If for instance, this is a drop, one drop, then the heat transfer that is taking place, assuming that this, let us say the air is hotter, the heat transfer is taking place from the air to the water like this across each drop that we are seeing here. The red arrows show the direction of the heat transfer. If the air is hot, it is flowing upwards, and the water is cold and it is flowing downwards in the form of drops. So, there is no metal wall separating the two as we had in a direct transfer type of heat exchanger. So, we call it a direct contact type of heat exchanger. So, these are three broad types of heat exchangers. Now, during these few lectures that we have, we shall be concerned only with the first type, that is the direct transfer type of heat exchanger. I mean, we could have looked at others, but generally for an elementary undergraduate course, it is adequate to look at the direct transfer type of heat exchanger. Now, let us talk a little more about the direct transfer type of heat exchanger. Direct transfer type heat exchangers can be broadly classified as belonging to one of three categories. What are these? We call them as, one category is what we call as tubular heat exchangers. A second category is what we call as plate heat exchangers, and a third as extended surface heat exchangers. Tubular heat exchangers, plate heat exchangers, extended surface heat exchangers. They are all direct transfer type heat exchangers, mind you. That means they follow the basic definition that we gave earlier. Both fluids are flowing simultaneously through the device. There is some wall separating the fluids. Heat transfer is taking place across that separating wall or walls. So, that definition is satisfied, but depending on the shapes that we use, we give these names. We call direct transfer types as tubular heat exchangers, plate heat exchangers, or extended surface heat exchangers. Now, let us look at each of these. First, tubular heat exchangers, and in fact, we have already looked at one tubular heat exchanger. What was that? That was the concentric tube or the double pipe heat exchanger. We have already looked at that, one tube inside another tube, the hot fluid, one of the fluids flowing through the inner tube, the other fluid flowing in the annulus around the inner tube. We have already seen that. Now, let us look at one more tubular heat exchanger, and that is called the shell and tube heat exchanger. So, we are now going to look at another type of a tubular heat exchanger, which is called as a shell and tube heat exchanger. Now, let me first show you a sketch of a shell and tube heat exchanger and describe it. A shell and tube heat exchanger typically consists of a cylindrical shell, that is what we have here, okay, and a bundle of tubes inside the shell. I have shown here 4 tubes, 1, 2, 3 and 4. You follow? There are actually many. We are just showing it is a sketch. So, we are showing 4. It is a bundle of tubes inside a shell. The tubes, the axis of the tubes is parallel to the axis of the shell. All right. One fluid flows inside the tubes, and that is the fluid that I am showing here, entering here. It's breaking, the flow is breaking up into 4 parts, going through each of the tubes that I am showing, flowing through the tubes, coming out here and then going out. So, this is one fluid going inside the, flowing inside the tubes and coming out. All right. The other fluid flows on the shell side, that is outside the tubes. It enters the shell here, all right, flows outside the tubes in the shell space outside the tubes, and in this case you can see it is flowing on the outside of the tubes and then exiting through an outlet at this point in the shell. All right. So, that is the second fluid. Now, there are some more parts inside this which I want to describe. First of all, let me again repeat. The two main elements of the shell and tube heat exchanger are: number 1, a cylindrical shell; number 2, a bundle of tubes. I have shown 4 here. It will actually be a bundle whose axis is parallel to the axis of the shell. So, that is 2. Then the tubes are fixed in sheets at the ends here, and these are usually called as tube header sheets. So, what we are seeing here at the ends here, these are called tube header sheets in which the tubes are fixed. Then we have the front and the rear ends of the heat exchanger. This is one end of the heat exchanger, this is another cap at the end of the heat exchanger. So, these are called the front and the front and the rear end heads of the heat exchanger. The fluids enter through inlets. As you can see, this is the tube inlet for the tube side, this is the outlet for the tube side, this is the inlet for the shell side fluid, this is the outlet for the shell side fluid. These are typically called nozzles. These 4 are called nozzles. And finally, in order that the shell side fluid should flow over all the tubes properly, usually sheets are placed across the flow, and which make the shell side fluid flow in this zigzag fashion, as you are seeing here, which ensure a zigzag flow on the shell side, and these sheets are called as baffles. All right. So, these are the main elements of a shell and tube heat exchanger. I repeat, the tubes which are enclosed, a bundle of tubes enclosed within a shell, the tube header sheets, the front and the rear end heads, the nozzles, 4 of them, and baffles which ensure a good flow on the shell side of the shell side fluid. One of the characteristics to describe a heat exchanger is the amount of heat transfer area it provides per unit volume of the heat exchanger. Typically, a shell and tube heat exchanger will provide anything from 100 to 500 square meters per cubic meter of volume of the heat exchanger. Okay. So, keep this in mind whenever you are thinking of a shell and tube heat exchanger. Now, let me again show another transparency just to repeat the same things. The major components of a shell and tube heat exchanger are a bundle of tubes, the shell, the tube header sheets, the front and the rear end heads, nozzles and baffles. The heat transfer area available in a shell and tube heat exchanger per unit volume can range from 100 to 500 square meters per meter cubed. All right. Now, I am going to show you a typical tube bundle in a shell and tube heat exchanger. There you see it on the screen. All right. Now, what you have got on the screen is a typical tube bundle. I told you there is a big bundle of tubes. In this case, as you can see, you got 3, 6, 9 and 16 and 24 and 7, 31, something like 50 tubes or a little more than 50 tubes making up this heat exchanger. All right. This plate at the end is the header sheet, the tube header sheet which I described, in which the tubes are fitted. This is the other tube header sheet at the bottom, and you can see it is on a flange there because it has to be fixed to the rear and the front or the front end head of the heat exchanger. And here you can see the baffles. You see, this is a baffle, this is a baffle plate, this is a baffle plate, to ensure that the shell side fluid flows in a zigzag fashion on the shell side and flows across all the tubes of the heat exchanger. So, I have taken out a tube bundle to show you, so that you get a pictorial photographic view of a typical shell and tube heat exchanger. All right. So, this is a typical shell and tube heat exchanger. Now, let us move on. We have described the tubular heat exchanger, and what did I say? First we looked of course at a concentric tube heat exchanger, then at the shell and tube heat exchanger. Now, we want to look at the next one, and that is a plate heat exchanger. A plate heat exchanger, as its name says, is nothing but a series. In a plate heat exchanger, we have nothing but a series of large rectangular thin metal plates which are clamped together to form Now, we look at the next type of direct transfer type of heat exchanger, that is the plate heat exchanger. A plate heat exchanger, in very simple terms, is nothing but a large number of thin rectangular metal plates. A series of large rectangular thin metal plates which are clamped together to form narrow parallel plate channels. That is what is a plate heat exchanger. And in order to illustrate this, let us look at a photograph which I have here of a parallel plate heat exchanger. Here is a parallel plate heat exchanger. Now, in the parallel plate heat exchanger, okay, these are the plates which I am showing here with the cursor 1, 2, 3, 4, 5. These are the plates. These are the end plates which are helping to clamp all those thin metal rectangular plates together. Alright. So, we have a series of passages which are in the form of parallel plate channels, like this is number 1, number 2, number 3, number 4, number 5, number 6, 6 parallel plate channels. One fluid, let us say the one with dots here, is entering here, alright, and flowing through these channels, number 1, number 3 and number 5. It is going down through number 1, going down through number 3, going down through number 5, then it is being, there are ways in which they all join together and coming out at this point. The other fluid you can see is entering here, okay, and there is an arrangement inside so that it automatically gets directed into passages number 2, 4 and 6. You see that there, and it goes up through each of these passages. This is passage number 2, this is passage number 4, this is passage number 6, and then they again link up, the flow is all linked up together and it comes out. So, basically here we have a 6 parallel plate channel heat exchanger with one fluid flowing through channels 1, 3 and 5, the other flowing through 2, 4 and 6, and heat being transferred from one fluid which is hotter to the fluid which is colder than it. Alright. So, this is what we call as a parallel, as a plate heat exchanger. Typically, for such a heat exchanger, the heat transfer area that you would get in such a heat exchanger is the heat transfer area per unit volume for a plate heat exchanger would typically be from about 100 to 200 square meters heat transfer area per unit volume of the heat exchanger. Alright. So, this is the second type of heat exchanger, the plate heat exchanger, a series of narrow parallel plate channels. Now, the third is what we have called as the extended surface heat exchanger. Let me first describe it. Fins are attached on the primary heat transfer surface with the object of increasing the heat transfer area, and as a result, because of the fins, one provides much more heat transfer area per unit volume than a tubular or a plate heat exchanger. Typically, in an extended surface heat exchanger, because of the fins, one has more than 700 square meters of heat transfer area per unit volume of the heat exchanger. Compare this with the numbers that I gave you earlier. Alright. So, you put fins on the primary heat transfer surface in order to enhance the heat transfer area per unit volume of the heat exchanger. Now, again let us look at some sketches to illustrate ideas. Here is what we call as a plate fin heat exchanger. So, it is a plate heat exchanger, but with the fins added on, it becomes really an extended surface heat exchanger. So, here are the channels now, as you can see, here are the channels. This is, there are here 1, 2, 3, 4, 5, 6, 7, 8 and 9 plates, and you can see if I start numbering the channels from here, channels 1, 3, 5 and 7 are one set of channels, and 2, 4, 6 and 8 constitute the other set of channels. 9 plates giving us 8 channels, 4 for the hot side, 4 for the cold side. Alright. And it is not just channels that we are providing, but you can see that we are providing fins which are interconnecting the one side to the other. That means, they are long thin strips which are inside these channels, which are connecting one side to the other and providing this much more heat transfer area. So, the fluid flowing through has to flow through narrow passages, narrow in this direction, narrow in this direction as well, all right. And the same is also true on the other side. We have got fins also on the cold side here, and so there are narrow passages, narrow long rectangular passages on the cold side as well. So, as a result you provide a lot more heat transfer area per unit volume, and what we are showing here is only the core, mind you, of the heat exchanger. In reality, there would be some manifold at the end here, a manifold at the end here, a manifold on this side. So, the hot fluid enters, gets distributed into these channels, comes out at this end, gets collected and then flows out. So, it is not just it is not the whole heat exchanger. What we are showing you is just the core. Now, I want you to show you a typical core of a real physical model, and here we go. This is a core of a plate fin heat exchanger, or what is broadly called as an extended surface heat exchanger. Okay, here you again see we have got in this case 1, 2, 3, 4, 5 channels here, and you can see in between the plates we have these fins which are attached. They are not all equal in size, but these are the fins which have been attached in between. Okay. This is one side, and then if I go to the other side, here we have the other side of the heat exchanger, where you can see I have the other fluid flowing through these channels which are slightly narrower in width, and again we have fins here. So, it is an extended surface heat exchanger, or to describe it in terms of its geometry, it is a plate heat exchanger with fins. So, we call it a plate fin heat exchanger, and again this is only the core of the heat exchanger. One gas typically would flow through this side, through these channels, these 4 channels, the other would flow through these 5 channels. One would be hot, the other would be cold. Heat would be transferred from the hot fluid to the cold fluid. All right. Now, let us look at some more examples of extended surface heat exchangers. These are what we showed just now was a plate heat exchanger with fins, a plate fin heat exchanger. You could also put fins on tubes, in which case we get what are called as tube fin heat exchanger, and here we have 2 types of tube fin heat exchanger cores. Now, here is a bundle of tubes. Look on the left side, these are 3 tubes like this, all right, and one fluid is flowing on the outside of the tubes like this, the 3 vertical arrows. The other fluid is flowing inside the tubes. Typically, this type of heat exchanger is used for exchanging heat between a gas and a liquid. So, the liquid will flow inside the tubes, because the liquid you already have a high heat transfer coefficient. On the gas side you do not have a high heat transfer coefficient. So, in order to enhance or reduce the thermal resistance on that side, we put fins on the gas side. So, this is called a tube fin heat exchanger. Now, a typical either the fins can be on individual tubes, as you are seeing here. These are round fins on each tube, and they will be closely stacked together, or you have got a continuous fin sheet like you are seeing here, and the bundle of tubes is like this, through which the liquid is flowing. So, this is also possible, in which case you have continuous fin sheets fixed on the array of tubes, or here individual fins on each tube making up the tube array. This is typically what we have in an automotive car radiator. We have the tubes through which the hot water flows, and these are the continuous fin sheets through which air is pulled, and that helps to cool that hot water which flows back to the engine of the car. So, an automotive radiator is typically of this type. A continuous fin sheet on an array of tubes is what constitutes what it is a tube fin heat exchanger, and it is a compact heat exchanger in the sense it provides a lot more heat transfer area per unit volume. We can also classify direct transfer type heat exchangers by the flow arrangement. We can use that also as a description of a direct transfer type heat exchanger. Like we have described them in terms of the geometry, when we say they are tubular, or we say that they are plate heat exchangers or extended surface heat exchangers. Similarly, the way in which the two fluids flow relative to each other is another way of classifying direct transfer type heat exchangers. So, let us classify them now by their flow arrangement. There are three basic flow arrangements, and what are these? The three basic flow arrangements are parallel flow, counter flow and cross flow. We want to describe each of these carefully. Let us look at each of these carefully. Now, first let us look at parallel flow. First let us look at parallel flow. I am going to describe the parallel flow arrangement with respect to the concentric tube heat exchanger. Concentric tube heat exchanger. This is one tube inside another tube. Now, let us say this is the hot fluid flowing through the inner tube. It is flowing in at this point. All right. So, we say hot fluid flowing in at this point, and it is flowing out at this point. So, let us say this is hot fluid flowing out at this point. Out and in. Now, the cold fluid comes in at this point. Let us say this is cold fluid in and goes out at this point. All right. So, now notice the two fluids, the hot fluid and the cold fluid, are both flowing parallel to each other in the same direction along the length of the heat exchanger. The hot fluid is flowing through the inner tube like this, and the cold fluid is flowing through the annulus like this. Since they are both flowing in the same direction, we call this a parallel. When they are both flowing in the same direction, we call it a parallel flow arrangement. All right. And of course, as I mentioned earlier, the heat transfer is taking place through the surface of the inner tube. This is the heat, where the heat transfer is taking place from the hot fluid to the cold fluid across the surface of the inner tube. So, this is why we call it a parallel flow arrangement. On the other hand, if I reverse the flow of one of these fluids, then I will get a counter flow arrangement. So, all I have to do now for a counter flow arrangement is to reverse the flow of one of the fluids. So, let us say now this is still the hot fluid in, we will call this still hot fluid in, and going out here hot fluid out. But now the cold fluid enters at this point. So, we will say this is cold fluid in, and leaves at this point. So, now notice the hot fluid flowing through the inner tube is flowing axially in this direction. the cold fluid flowing through the annulus is flowing in this direction. All right. They are flowing in opposite directions, both parallel to the axis of the heat exchanger, but in opposite directions, and that is what we call as a counter flow arrangement. The heat transfer, mind you, is still taking place in the same way from the across the surface of the inner tube. There is no change there, but the direction of the two fluids relative to each other is different. So, this we call as a counter flow arrangement, when the two fluids flow in opposed directions. The third type of basic arrangement is what we call as a cross flow arrangement, and let me describe that for you now. Next, in a cross flow arrangement, the two fluids basically flow at right angles to each other, like this. Let us say this rectangle which I am showing is part of some heat exchanger. It is a plate which is part of some heat transfer surface, and the hot fluid, let us say, is flowing on the back side of this plate. So, we will say this is hot fluid in, and flowing out here. So, let us say the hot fluid is flowing on the back side of this plate, and the cold fluid is flowing on the front side of this plate here, like this. So, we will say cold fluid in. And flowing out. Like this. So, we say this is cold fluid out. Now, this is a cross flow arrangement in which the two fluids are flowing at right angles to each other. All right. One, in this case, this is the heat transfer surface, which is the plane of this paper. One fluid is flowing maybe in front of this paper, one fluid is flowing at the back of this paper. Now, let us go back again to the plate fin heat exchanger, which I showed you earlier. All right. Here is the plate fin heat exchanger, which I showed you earlier, and let us look at it again for a moment. Okay. Now, look at it. This is one fluid which will be flowing like this, and this is the other fluid which will be flowing through like this. So, this is a cross flow arrangement that we have got here. Now, there is something more which I want to also say. This is a cross flow arrangement, but mind you, in addition, what is to be noted is we have got fins here. Now, when you have fins which are in this heat exchanger on both sides, both on the hot side and the cold side, a fluid particle which enters here, say in this passage, will go through the heat exchanger and come out at this end here. It has no choice. A fluid particle which enters here has to come out at this point. A fluid particle which goes in here has to come out at this point. You understand? Because the fins make passages right through along the length of the heat exchanger. Now, when this happens, when the fluid, let us say this is the hot fluid, enters like this with fins on it, it is forced to move in not only between these plates, but also in the particular passage which is created by the fins which are right here. So, this hot fluid cannot move in a transfer direction inside these channels. Similarly, this is the cold fluid. Once it enters here, some cold fluid enters here, it has to stay in that passage and move along the length of the heat exchanger. It cannot move crosswise in a transverse direction inside this parallel plate channel. So, the presence of the fins in the parallel plate channels prevents any transverse motion of the fluids, either the hot fluid in its own channel or the cold fluid in its channel. You follow? Now, when this happens, we say this is cross flow, both fluids unmixed. Unmixed means not mixed with each other, but cannot mix in a transverse direction. No fluid in a direct transfer type, the cold fluid does not mix with the hot fluid. So, when we say unmixed, we mean mix with each other, it cannot mix with each other. So, the both fluids unmixed is the situation that you will get when you have fins on both sides like this. Now, suppose I do not have fins on both the sides, but I just have parallel plates. Then in that case, a hot fluid entering in this channel can, while flowing through, can also move in this direction and mix with itself, in which case we will say this is a case of single pass cross flow, both fluids mixed, because there are no fins on either side, the fluid can mix with itself. And if I have fins on one side and no fins on the other side, then it will be a case of single pass cross flow, mixing on one side, no mixing on the other side. So, in single pass cross flow, it is possible to have flow arrangements in which the fluids can either mix with each other or not mix with themselves. Now, therefore, we say there are three possibilities in single pass cross flow, and the three possibilities are cross flow unmixed on both sides, cross flow mixed on one side, unmixed on the other side, cross flow mixed on both sides. When there are fins, it is unmixed on both sides. When there are no fins, it is mixed on both sides. Keep that in mind. So, in cross flow also there are three categorizations possible. Now, there are three one point which is worth noting is that generally if we calculate the heat transfer area for these three arrangements, that is parallel flow, counter flow and cross flow, if we calculate the heat transfer area, typically we will find that the heat for a given situation and we want to transfer a certain amount of heat, typically we will find that in parallel flow you need the maximum area, heat transfer area, in counter flow you require the minimum area, and cross flow, whether it is unmixed on both sides or mixed on both sides or mixed on one side, unmixed on the other, will require an area in between these two extremes. So, keep that in mind as something which is a rough idea of what will be the sizing that we get of heat exchangers in a given situation. Now, let us talk a little about the overall heat transfer coefficient and fouling factor. In a heat exchanger, in a direct transfer type heat exchanger, suppose there is a plane wall. From your study of conduction, you know that in a plane wall there are heat transfer coefficients on the two sides, H1 and H2, and if B is the thickness of the wall and K is the thermal conductivity of the wall, then the overall heat transfer coefficient is given by 1 upon U is equal to 1 upon H1 plus B by K plus 1 upon H2. And if it is a tube, like in a shell and tube heat exchanger or a concentric tube heat exchanger, the overall heat transfer coefficient 1 upon U Ri will be given by 1 upon Hi plus Ri by K log to the base E Ro by Ri plus Ri by Ro 1 upon Ho. Now, these equations for calculating the overall heat transfer coefficient, where H1 and H2 will come from our knowledge of convection, mind you, or Hi and Ho will come from our knowledge of convection. These equations for calculating U are valid for clean surfaces. In practice, with the passage of time, solid deposits usually tend to accumulate in the form of thin layers on the surfaces on the heat transfer surface, and these deposits present an additional thermal resistance to the flow of heat. Now, next time we will talk about how to take account of this additional thermal resistance that comes in when because of the thin layers which form on the heat transfer surface. This formation of thin layers is called as fouling, and we account for it by what is known as introducing fouling factors in our expression for the heat transfer coefficient. Next time we will look at that aspect.